Few minutes, we get ready, and we're almost ready to go. Thank you.
Hi, everyone. Oops, there. Okay, I'll stand by the speaker. Thanks, everyone, for coming. John and Lou have been, I don't know, friends for quite a long time. And anyways, I'm just going to read from John's own Wikipedia or Canberra page that says, I grew up in Chicago. Are we okay? I'll stand by the speaker. Everyone for coming.
Start again. Now it's fine.
Now I can try again. Sorry about the double repetition. Where he says, I grew up in Chicago and studied and worked as a geologist in the US before moving to Australia in 1994. Since moving to Australia, I've spent all my time teaching at teaching ANU undergrads and working in the experimental petrology group. So I'll give it a short introduction and hope we're going to get some experimental petrology.
Okay, good. Thanks for that, Sue. Thanks, Lou, for inviting me. See what the device does. Okay. I've been working on carbonatites and related rare earth deposits for a few years now, mostly working on Australian deposits. Although recently we've been working elsewhere. So I just wanted to just go through a few things and just briefly talk about why we care. Carbonatites are strange rocks, and I won't pretend that I know where they come from or why they come from or what they really do. My interest comes when they go up into the crust and they do things. But if you look around the world, you can see those little green dots there, and there's quite a few of them. And you can see how they're very close to cratons. I think we all know that, and especially being here in Africa, there's a lot of carbonatites here. If you look at the green dots in Australia, there aren't very many, which I think is rather odd for such a big country to have so few. And considering that we have some very old rocks in Australia, it is an interesting thing. Also, just like with kimberlites and alkaline rocks, you can see how their numbers and abundance have been increasing with time. And as you know, those rocks are all associated in some weird and wonderful way that I have no idea why, but they are. But those that have associated rare earth deposits are rather few. They're the red dots on this diagram. And if you look around the world, you see that there's some in Asia and there's a few others. But the two I really want to point out here are Mountain Pass here. Does this pointer work? Okay, there we go. Mountain Pass here on the border between California and Nevada. And then Bayanobo here in Inner Mongolia and China. These are the two biggies, so keep them in mind. I'll talk a little bit about those before I carry on. Here we go. I'm fine with moving it. Okay, good. Thank you. Okay, so if we look at rare earth production, we see that in the early days, from the 60s through sometime in the late 90s, almost the entire resource production of rare earths came from the US, and that was Mountain Pass. So one deposit. Since then, it's been taken over by one other deposit here in China, the big red one, which is Bayanobo. Both of these are carbonatite related. So it turns out that if you want to know about rare earth deposits, you pretty much need to know about carbonatite deposits. There are many other kinds of rare earth deposits, which I won't go into because that's not what I'm here to talk about. You've all seen this, big increases in, the green economy of the future, mostly in, rich Western countries. But for whether you like it or not, they're increasing dramatically. And they have one thing in common. Wind turbines and magnets make these. So rare earth permanent magnets are the thing that does everything. These are miraculous gadgets. They are such strong magnets and such permanent magnets that if you put the current through them, they become a motor. If you have the wind drive them, they generate electricity. So these things are a big deal. And here's the composition of them. We call them NdFeB magnets. And this is sort of the formula, although everybody has their own mix. But the important thing is here, there's a lot of neodymium and praseodymium in there. Something like 35% of these magnets. So this NdPr is what we're after. There's a little tiny bit of dysprosium and terbium in there, just for a little taste. So that these four elements, as I'll show you, are the ones that people want. And that's a bit troubling because if you want rare earths, you don't get to choose which one you get. You get all of them. Now, this is an interesting thing. If we think about the multi-trillion-dollar net zero opportunity that the world is supposed to have, we look here and we say, okay, we need a lot of copper. We know that. Aluminium, lithium, steel, nickel, cobalt, and this little tiny yellow sliver there is rare earth. So it's really not a big market. It'll never be a big market, but it's crucial. The whole thing depends on the rare earths. This is why people call them critical and get all upset about them. All the governments all over the world are freaked out about rare earths. And they're in everything, right? But what I really like is that in a passenger vehicle, which is something like a $2 trillion business, if you look at all the gadgets in it, those are all rare earth magnets. And it's rather interesting. In some of these things, like we can't even bother to change our rear view mirror anymore. We have to be able to push a button. All of those buttons you push in your car, when you open the sunroof, everything you do is a rare earth magnet, which means it's a growth industry. Okay, carbonatites. This is just some data that I grabbed off the web, but they all look about the same. As you can see here, they're very much enriched in barium, and they're very much enriched in strontium, and you can see how the rare earths are fairly high. But the thing that's unfortunate maybe is that all the carbonatites slope from left to right, which means the most abundant rare earths in them are lanthanum and cerium. And this is unfortunate because we don't have a lot of uses for lanthanum and cerium. And in fact, if we weren't pumping it down oil wells in Texas to keep them flowing, I don't think we would know what we would do with them. So I looked up last year the price of, for instance, cerium, and it was $2 a kilogram. I went to the grocery store and I went to the hardware store, and I couldn't find anything that was cheaper than that. Flour, sugar, sand, you can't give this shit away, right? Cerium is just one of those things we don't want. On the other hand, if you look at, for instance, terbium, it was $2,000 a kilogram. So that the difference in price here is extreme. And that's the tricky part of this business, that you get all of them and you got to find something to do with them. And this isn't the best thing. So to show you of the value that you could sell it for, 90% of the revenue comes from NdPr, terbium, and dysprosium. So that when people think about rare earths, they're thinking about those four elements. And I imagine in the future, we'll probably find more things to do with the others. Like there's also a samarium cobalt magnet, and there's some other things we can do. But okay, let's start talking about carbonatites. You've all seen this slide. You know more than I do. I have walked up to the top of Lengai, and one of my PhD students will be, I think, starting to walk up there tonight. So good for him. You go up there, it's beautiful. You get to look down into the red bubbling stuff. And then mostly you just have this muck that's pouring down the hill. So this is a natural carbonatite. It's mostly just sodium carbonate, right? You can put it in food. It's nothing special, really. So just to reiterate that our past use is entirely dominated by two big deposits. And the question is, how long will they last? Notice how Mountain Pass for a long time went out of business, and now it's coming back. If you look at the trends, and I know we're bad at forecasting, but the trends are that they're probably going to increase. We're going to want more and more rare earths. So I was just going to talk about a few. The biggest one on Earth, Bayan-Obo, that is Inner Mongolia there, that red dot. It has dominated the world, and in fact, there's a huge city next to Bayan-Obo that is where most or almost all of the world's magnets are made. So they're all controlled there. So not only do they have monopoly on the source, they control the use. So one of the issues we have is that if you develop a rare earth project, it's most likely that the minerals are going to end up in China, end up in a magnet, which we'll buy back to use in our cars, etc. It's a huge complex, and it was mined for many years for iron. There's a lot of iron. But the thing about it is that I was just mentioning is all the rare earths kind of look like this. There's something like 50% cerium. And if you look at praseodymium and neodymium together, it's about 20% of the total rare earths. That's a decent number, and it's typical of carbonatites. So people will often talk about the NdPr ratio, which just means divided by total rare earths. And so this is mostly what you get with a carbonatite. So that you got all this other stuff you don't really want. Notice how 77% of it's cerium lanthanum. But the other ones are a bit rare. And if you look at the host rocks, it's dolomite. And one of the fun things is that if you look at all the dikes that are cross-cutting through there, it turns out that the really valuable stuff is in these carbonatite, really rare earth rich dikes. And what's funny is that if you look down the lower right here, that you can see at Bayan-Obo, we've got a vein of carbonate going through carbonate. And I'll talk a little bit later about why that's a good thing, why this is the richest deposit on Earth. I said there before that this vein here is 28% rare earth. That's ridiculously high concentration. Most carbonatites, if they've evolved enough to get high in rare earths, are about 2 or 3%. So overall, this deposit isn't 28%, but it's something like 8, which is rather valuable. So it's been interesting over the years that I've sort of followed it, that the range of genetic models for Bayan-Obo are quite insane. Syngenetic sedimentary deposition, I don't think so. Right? Metasomatism associated with granite magnetism, no. Right? Deposition from exhalative, possibly carbonatite-related hydrothermal roof, no. Epigenetic origin via multi-stage hydrothermal, no. All these things they've been through, and they finally settled on something related to a carbonatite, right? And so it's interesting that Bayan-Obo took sort of 20, 30 years to realize that it really is something related to carbonatite. And oddly enough, Mountain Pass was the same thing. They fought for decades over whether this really is a carbonatite or not, because they're difficult things to work on unless they're the simple ones. Okay, so let me talk a little bit about Australia. This is showing you a compendium of all the carbonatites that have been identified in Australia. And this was put together by Ross Chandler. And he looked and looked and looked and could only find 21 carbonatites in the whole continent. And if you notice, the young rocks here in the east don't have any. And you can see here, there's the Eastern Yilgarn, there's the Gascoyne, there's the Halls Creek in Lyre, and the Arunta. These are all major breaks in the continents with huge, geophysically identifiable, deep, deep faults. So people have put together the idea that these things form in these big sort of major continental faults, and they're along these trends, as you can see here. So I'm going to talk a little bit in detail about one of them from here and another one from the Gascoyne. We've worked on some of these others, but I won't talk about them today. So that these are the big structures and the carbonatites on them. And one of the things that's neat about Mount Weld is, because of all the magnetite in it, they are a rather simple magnetic structure, as you can see. And notice how here is the big fault next to that. And you can see how there's a few of them around here. And this is a very large, very rich deposit. So it's 5.5%, 55 million tons. It was found in the 60s, but they never really developed it until more recently. That's the case with most carbonatites. And many of them were first discovered when people were looking for uranium. Because as you may or may not know, uranium and thorium go with the rare earths. This is a good thing and a bad thing. One of the reasons the US got out of the business in the 80s was that environmental regulations meant that companies didn't know what to do with the thorium. And so they decided they might as well offshore it until they realized that a monopoly was set up, and now they got to figure out what to do. The whole world's thinking about how you can handle it. But nonetheless, this is a seriously large deposit. And mostly, if you look down the right here, it's mostly the weathered material on top of it. Because it's 2 billion years old, it's been sitting there weathering away for a long time. It's deeply weathered, and during that weathering process, it really concentrates the rare earth. Because they're immobile, when you weather them, they just build up. So you simply extract everything else, and the grade of the rare earth keeps increasing. This material on top is all piled on top. They have to strip that off. But it's just been initially a little pit, and they've just been mining the really simple stuff. Here's what it is more recently. It's getting bigger. They have many stockpiles of different sorts of ore. And I must say that one of the hardest things about rare earths is the metallurgy. No, this is Mountain Pass. Oh, sorry. Bayan-Obo is much bigger. Right? But what's interesting is that they've only been scratching around the surface of it. So that if you look at it, here's this giant carbonatite complex. And here's the little tiny pit in the middle of it. And here was the deepest hole that they had drilled until last year. And they put a deeper hole in it, and I said, oh, goodness, this thing keeps going forever. This deposit will just go probably as deep as they want to mine. So it's probably going to be around for hundreds of years. So here's what it looks like in cross-section. You've got metasomatized material, glimmerites and phenites. Glimmerites being the more mafic version, where you have biotite in the rock, and phenites where you're making potassium feldspars. And you have lots of country rock material decorated in there. And you've got a lot of calcite. All of this blue is calciocarbonatite. And in the middle is where we get into the magnesio ferrocarbonatite. So I'll go into this a little bit more, but calciocarbonatites rarely have any rare earth grade in them. And they're mostly the biggest part of the carbonatite. But they're a good thing, as I'll show you in detail, that you fractionate out calcite to build the rare earths up so that when you get to an evolved carbonatite, you can make a rare earth deposit. So just to give you a little bit of an idea here is, they like to plot calcium against magnesium and iron and manganese. And you can see how there's up here, the calciocarbonatite, and then we find ourselves evolving into a magnesio carbonatite and then a ferrocarbonatite. And that's the usual progression. And there's no surprise there. And as you can see here, you've got this amazing concentric thing where we had a huge volume of calcite. And then in the middle, we've got this little magnesio-ferrocarbonatite. It's hard for me to imagine how exactly that happens, but I'll show you some cartoons later that maybe explain that. What's weird here is that if you look at the total rare earths against niobium, you see that the things that are low in rare earths are rich in niobium. So that's the calciocarbonatite. And it's very typical for the calciocarbonatite to have the niobium and the rare earths to be in the more evolved carbonatites. And so just to make that point, here's the typical rare earth plot divided by chondrite so that we can have a spidergram because we like those. And you can notice the calciocarbonatites in blue here and the magnesio-ferrocarbonatites have orders of magnitude more rare earths. So obviously this is the stuff you mine or the weathered equivalent of that material. So just have a look at them, right? 80% by volume is calcium carbonatite. And you can see it has lots of xenoliths. It has lots of weird amphiboles and magnetite and phlogopite. And this is typical calcite, apatite, and magnetite. That's typical calciocarbonatite. And then there's a few weird veins that come through that we're not really sure what they are. It could be more evolved stuff than migrating through the calciocarbonatite, but still the grades are low, a total of 0.5% of TREO, and nobody mines calciocarbonatites. To get to the better stuff is the magnesio and ferrocarbonatite dikes, which cut through, and these are loaded with rare earths and get to very high grades. And you get into a whole bunch of these strange names, which I'll talk a little bit about, but there's something strange happened that the Russians and the Chinese were naming minerals at the same time. So they came up with craziest unpronounceable names. I have some Chinese graduate students and I say to them, how do you pronounce this thing? And they're not even sure, right? So I won't say their names, but nonetheless, there's an amazing array of carbonate, fluoro, strontium, calcium, barium, rare earth minerals. And I'll show you some more of them. Whole bunch of them sit in here. Anselite's one of them. There's a whole bunch of them. We don't have to worry about the names, but these dikes are full of them, as is the real live body of the magnesio ferrocarbonatites, where you have things like monazite growing into cracks in the rock. And so monazite there, and then there's syncosite, one and bastnasite. So these get to be really high grades. And so the core of this system is really quite rich. Gets up to 8%, that's sort of the number you're looking for. Okay, so another place that we've worked is up here in the Gascoyne. And in the Gascoyne, there's some very strange rocks there. So if you look at these little red lines here, these are ironstones. And they were first found up here in a place called Yenjabana. And they found a whole bunch of these ironstones up here that were quite rich in rare earths. Then they started looking south of this fault, and look at all these things. That's 16 kilometers of ironstones trending across this area. So those are those things we were working on. And in the field, it's just the most amazing thing because you get these veins of ironstone, and they're all just iron oxides of some sort and variety. And they're very rich in rare earths. And the explanation is that you've got dikes of carbonatite coming up, and they've evolved through the magnesium phase into iron-rich phase, and then they've been deeply weathered. They're 1.3 billion years old. So you end up with an ironstone on top of carbonatite that's quite iron-rich. And I'll show you some pictures of it. So here's the minerals that I was talking about, but I won't mention their names. But if you put them here, the most popular one is bastnasite, which is the normal sort of old barium. Oh, could you mute yourself, please? The language.
Ask the people in the audience in Zoom to mute themselves. Sorry. Thank you.
Thank you. Okay, thank you. So if you just plot the total rare earths against barium or strontium or all of them, they seem to plot on this nice trend, which I've always thought is kind of a cool thing in terms of we could maybe make a sort of a solid solution series and maybe come up with a better way to name them rather than this craziness. But that's for another matter. So if you get the rare earth patterns, again, divided by chondrite, you can see how these things are rather high, talking about, 10,000 times chondrite. And you can see that the monazite's quite rich, the rhabdophane, which is hydrated monazite, and then these crazy things down here. But one of the things I want to point out in a minute is that one of the special things in the Gascoigne is that the NdPr ratio is quite high, which is a good thing. And we've been struggling with trying to figure out how that happens. And one of the things we noticed was that the fluorapatites, which are quite abundant in most carbonatites, notice how these things come up. In other words, there's less cerium and lanthanum than neodymium. NdPr is higher. We're still trying to figure out why that is. We're figuring something stripped it out. But that's the goal here, is to find carbonatites where the NdPr ratio is high rather than low. So here's a plot that's showing you that some of these phases get up to 30, 35%. That's a really good number. If you can do 35%, you're going to make some serious money. Here's what the stuff looks like. Here is the altered wall rock. Here's some crystallized material between it, and you get to the fresh carbonatite. You come further up, this is where it gets really siderite rich. So this is a high-grade ferrocarbonatite. And then this is the partially oxidized. And then you come up into this, which is just ironstone. All of these carry grade. And what's interesting, if you're looking at a magnesio or calciocarbonatite and you weather it deeply, you can increase the grade of rare earths by 300–400%, because all you do is go to just get rid of all the CO2 and carry all the calcium away, but the iron stays there. So you can only increase by maybe twice, because the iron just clogs it up and stays there. But nonetheless, this ironstone here is loaded with high grades of rare earths. And so this is something I stole from somebody. I really want to do this one on the right, is where they plotted out in a number of places where you could see an evolution from calcio to magnesio to ferro. And that's the story. And that's the key here, is that you need to evolve these things. So just like you have to evolve a silicate magma to get high concentrations of things, carbonatites need to do the same thing. And people have thought about what these things look like. And what we think the model for the Gascoigne is the Gascoigne is these things that are coming off the sides of a large magma chamber. So you get all of these dikes ringing around the intrusive. Whereas something like this is more like what you're seeing at Mount Weld and probably Bayanova. But we're still trying to work out where the best grades are and what to be looking for, because there's lots of carbonatites. So one of my students, Michael Annenberg, did some crazy experiments, as he likes to do. And I have to work through this. It's a rather complicated diagram, as most of Michael's diagrams are. What he did was, he did an experiment where he mixed up just carbonatite with silica added, carbonatite with sodium added, and carbonatite with potassium added. And he doped them with lanthanum and dysprosium. So he had a light and a heavy to see if he could tell what the difference might be. And if you notice here in just the straight up carbonatite, you crystallize a lot of apatite. This is a whole apatite, this yellow stuff here. And then you get a little bit of the goodies here in a few phases, but they're not highly concentrated. If you put silica in, it changes everything. And so this is telling you that you get a lot of clinopyroxene, olivine, biotite, and apatite. So the game changes completely whenever there's silica around. And keep in mind that, as I'll show you later, that carbonatites do react with the wall rock and they do assimilate silica, and that greatly affects what happens to the deposit. If we come down here to the sodium version, you can see that as this experiment cooled, it crystallized inward. And so both this one and the one below it, that you start with calcite and then you go through to dolomite. And so we're evolving inward on both cases, apatite plus calcite. Then you come out here to the magnesio dolomite and eventually other things. But what he found was that he cooled this from 800 degrees down to 200. When he got to the end, all of this red stuff was left there in the middle. And that is one of these really dysprosium-rich carbonate phases. And so this is the really juicy melty, we don't know what the hell it is stuff that is what you make a rare earth deposit out of. And I'll talk a little bit more about this in a bit, but people are starting to call this stuff brine melt. And the concept is that in the silicate world, we thought of silicate magmas, hydrothermal fluids, and there was one or the other. In pegmatites and probably in carbonatites, people are starting to think there's an in-between phase. That is a briny, melty thing that carries the rare earths. So that there's never really hydrothermal rare earth deposits. There are very few in the world. What they are is they are magmatic, associated near the body. And what we found was really odd was that the potassium experiments had more dysprosium in the stuff, and the sodium ones had more of the lanthanum, this phase here. And we're still trying to work that out. But this is essentially an evolving carbonatite evolving to really high rare earths. And notice how nothing is in these early phases. No rare earths in the early phase stuff, everything in the last gas. And that's a key point I want to come back to. Okay, so here's a diagram you made up just to review this. If you put silica in, that allows you to put the rare earths into apatite, because you can't put rare earths into apatite by itself. It has to have a charge balance. So you either put sodium or silica in with it. So notice how here he's got a diagram here showing apatites full of rare earths. So early forming things, that's bad, because you're just going to waste it all on the apatites, and you might get a little bit of deposition. So in the case of Bonobo, where we have dolomite intruding dolomite, it's the perfect situation because we don't have the silica interference. And so we can have this situation where this is the potassium and sodium without any silica. And can you notice how nothing goes into the early apatites? And then we evolve to this phase, berbenkite, which is a very rare but very abundant mineral that you don't see often because it weathers. It's just sodium carbonate with a lot of rare earths in it. And then you can have some heavy rare earth metasomatism and some veining around them. This is why Bonobo is such a great deposit. And as Lou said the other day, what are the chances you're going to have dolomite intruded by molten dolomite? Right? You did. He's probably forgotten already. Yeah. So anyway, this is sort of showing you that in a just a calciocarbonatite without much else in it, you don't do much. It hangs around the carbonatite, mostly low grade. That it's in these situations where you have really, really alkali-rich brine melts that can bring the stuff out. Notice how we also drew a thing here where if there's a lot of reaction with wall rocks, then again, we're going to have the rare earths locked up in early apatites. We're going to lose it, and it's not as good a part. So this is what we're kind of looking for. Okay, so some guys recently published an experimental paper that I won't bore you with, but I just wanted to put you in their experiments on sodium carbonate. They said that REEs being sufficiently concentrated in the brine melts to form economic ore bodies. So this is now what the world's starting to look into is, what is this phase and how do we deal with it? Where do we find it? How do I identify it? Okay, so back to this. Everybody always said it's a natural carbonatite. What's that all about? Well, I think we now know that somewhere along its path, it's crystallized out a hell of a lot of calcite and dolomite and anchorite and siderite. And then all you're left with is sodium carbonate. And here's a phase diagram somebody put together. It's a pseudo section, but it's a simple version because they didn't have magnesium or iron in it because those experiments are harder. But they show how if you're coming along here, you can have calcite plus liquid. Well, the liquid is here, and you can crystallize huge amounts of calcite until you evolve all the way down to here, where you get the sodium carbonate component. And this is the stuff that you extrude at Lengad. Or you use it up in wall rock reactions or doing metasomatism. And when you do that, this is an interesting concept we have, is that if you develop these really alkali-rich fluids at the end, and they then go into the wall rocks, then you crystallize everything because it's the sodium that's lowering the eutectic. So this is a nice way to think about it. And if we could do the more complicated, and we're trying to, we would see that it would go calcium, calcite, dolomite, anchorite, siderite. And that's what we see in nature. Okay, Here's another wonderful, incredibly complicated Michael Annenberg diagram. He's very good at drawing these, but they take a little work. One of the things we've noticed is that up against silica-rich wall rocks, you crystallize things like, in this case, diopside. Large amounts of diopside shielding the carbonatite from it. Now, in a paper that we submitted some years ago, the reviewers didn't like Michael Annenberg's term, which was anti-scarring. Now, many people, when the reviewers don't like it, you take it out, but Michael is stubborn. He said no. And it turns out it's a very popular term, that every time you see carbonatites up against silica-rich wall rocks, they crystallize diopside, or if they're more evolved, look up here, we're crystallizing azurine. This is because by now, melt is very, very alkali rich, whereas down here, it's more mafic, it even has some olivines kicking them. And if we look here on the side of the diagram, he's got a whole bunch of calcites with apatite, and then we go into dolomite, and then we go into anchorite. So this is the evolutionary sequence coming up here. And then at the top, guess what's coming out the top? The completely evolved sodium-rich carbonate melt. And if you want to have an immiscible silicate, then you can have some sort of weird silicate coming next door. And I should mention that oftentimes there are strange igneous rocks associated with carbonatites. And there's lots of arguments about what it means. I once went to Magna Cove in Arkansas. It's a beautiful place, huge nepheline cyanide body with a little tiny carbonatite in the middle. And they've got all these weird rocks. Like I still have a piece on my desk of jacuporangite, which probably only 3 people on Earth know what it is. But it's a very strange rock that you find associated with carbonatite. Oftentimes you don't see them. And now we're trying to wonder, do you have to have them associated? Do you not have to? Do we just not see them? We don't know. But you can see that everything pretty much is accounted for. And you notice here in the middle here, he's got brine melt, he's got anti-scarrins, and we've got the whole story here in one beautiful diagram. Okay, so the reason I came to Africa this trip was there's a company exploring up in Malawi, and they've got this very big carbonatite. And so we went to go sample it. They've been drilling it. The company's called Lanthanine. They're an Australian company. So they gave us some money to work on it. Lovely place. And there's a picture of it. And just for scale, this is 200 meters. So this is like a mountain of carbonatite. And I was wondering, why would you have mountains of carbonatite? It's 140 million years old. Why is it still there? And I'll tell you why I think it is. I'll come back to that diagram. If you look on top of it, you can see carbonatite veins, which are sort of gluing together this amazingly brecciated phenites, metasomatized wall rocks. So we have a lot of silicates in there that's holding it together. And what's strange is that if you look near here, you see these weird textures. Not the best picture. These are just field shots. I don't have good ones yet. But there's stuff that the French called leopard rock here, which are these really, really, this is about 8 to 10% total rare earths. So this is a very rich rare earth deposit. And these little guys are sort of flowers of strontianite and green monazite. It's from Malawi, Kangangundi, all right? And so we're just starting to work on it, but it's an amazing place because if you look, it is a 1963 map. So the French and various people were in here interested in it. They didn't know why, they just thought it was cool. And you look at this big halo here, that's the phenites and glimmerites. And if you walk around, you see either just case bar metasomatized rocks or biotized rocks. That's it, all the way around it. And then these little plugs here of mostly magnesio carbonatite. And so this thing here is one of the richest deposits I've seen. It's running, like I said, 8%. And the strange thing is that these monazites don't have any thorium in them. So I mentioned before that one of the issues with monazite is you got to deal with thorium. So one of the reasons you don't process it in the US is because everybody's freaked out about thorium, whereas in China, not so much. Right? We can deal with it, right? And so they're thinking this might be an advantage here, and that this is a potentially very big deal for a very poor country of Malawi to do this. So I just wanted to then reiterate, those are most of my slides, I didn't want to go on too long, that we believe that this sort of process can explain nearly every carbonatite except for Palabora, which we don't talk about, because we don't know what Palabora is. Maybe someday. The only copper deposit in a carbonatite, very strange place, but all the rest of them seem to be mostly on this sort of theme, that it's an evolving magma, just like a silicate magma, and you can look at the phenocrysts and you can interpret what it's been through and how it's evolved. And we now know that if you want to get the good stuff, if you want to get the really rare earth rich stuff, you have to go to at least magnesio, if not ferrocarbonatite. And I'll stop there. Thank you. Yeah.
No.
Yeah. Yeah. Okay, so for those of you at home, Lou says that I claim that in Australia that we find them along big fault structures, whereas in much of Africa, they're just sitting in rifts. So what's the deal? Is that correct? Right. And the answer is, we don't know. Right. But one of the things that we're starting to think about is, why is it that, you know, lamprophirs, lamproites, kimberlites, carbonatites are all on a sort of, find them in similar places? And why would you find them on plumes in Africa or on the East African Rift? I don't know. That's a good question we need to try to answer. Do you have an answer?
It's got to do with the source.
Yeah.
It's an active source.
Yeah. Yeah, exactly. No, but then why are the Australian ones all sitting next to major?
Upside down.
Yes, that's our problem, isn't it? Yeah, exactly.
Got one. As a geophysicist, I'm very curious about the magnetic signature. You mentioned magnetite and
Yeah.
iron, and how closely is the magnetic signature tied to the enrichment?
Well, you know, you always get magnetite phenocrysts even early on, so that they're always iron rich, and it's very rare that you don't find a lot of magnetite, often around the edges. So they do stand out. Certainly the Australian ones, you can pick them up, not just with magnetics, but also with their strontium and barium amounts. So that they're kind of easy to find, except they can they can often be so small that it's really hard to pick up. How do we get questions from the audience? They usually. Any questions from you folks out there?
Is there a chat?
There is. There usually is.
Yeah.
That's how we usually do it.
Yeah. I haven't run one of these in a long time.
Yes. Yeah.
Maybe you have to close the.
Always have some.
Troth has a question. Can we unmute Troth?
Hi, can you hear
Hi,
me?
Troth.
Hi, can you hear me? Hi,
Yeah, go ahead, Troth.
thank you. Right. Thanks so much for the presentation. It's really informative, I must say. As I'm speaking now, I'm actually currently in Malawi, working on a similar kind of carbonatite ring structure, which is just sitting south of the Lake Chira, known as Tundulu and Natache complex. I don't know, Prof, if you ever visited that when you came to Malawi, but I understand that Kangankude is also part of the Chira Acarine province carbonatite, ring structures. And now looking at the ring structure that we've got at our project, which is Natache, next to Tundulu, it is more or less in terms of its morphology, it just looks like Kangankude. Of course, I haven't been to Kangankude. Should we assume that the kind of genesis could be the same with Kangankude because they're sitting in the same Chira Acarine province?
I don't know if it's safe to assume anything with these things, right? Because they come in so many different shapes and forms. They could be dikes, they could be swarms of dikes, they can be big intrusives. I don't know enough because we just went up there, we visited the place, we sampled it, we came back down here, and here I am. So you probably know more than I do about the region. But I think as we study it and publish on it, I hope we can help characterize it, and maybe you could see if it turns out to be like the ones you're working on.
Okay, thank you.
Thank
I
you.
think I should get in touch with you.
Okay, feel free.
All right, thank you.
Yeah, so the question is that Paul Nex is pointing out correctly that there are often early euhedral phenocrysts of magnetites in these evolving carbonatites, especially in the calciocarbonatites. Then why do we have to wait till very late stage before we get to iron carbonates rather than iron oxides? And I don't know if we have an answer for that, but it's definitely true, and we see it often. Something to figure out. There's a lot to figure out. Yeah. Yeah, which one? Let me see. I gotta go.
I think minimize it.
So is it this one or?
Just repeat the question.
Do you know which one it was? Oh, I see. You want me to go this way? Okay. You mean sitting here, this positive anomaly? I believe the question is there is an anomaly sitting out here in the heavy rare earths. And I believe that's an interference that we need to correct out. The only anomalies we get is positive cerium sometimes, right? Yeah. And in super oxidized situation, we could see a praseodymium maybe, but that's it. Yeah. No, it's simply that Okay, so the question is, these rare earth-bearing ironstones, how do you make them? And the answer is you evolve the dikes to very high iron, and then you spend 1.3 billion years oxidizing and weathering, where you turn all the 2+ iron into 3+, and you leave iron oxide. It doesn't go anywhere, and the rare earths stay there with it. So it's a weathering superimposed on a carbonatite evolution sequence.
Just been told there's a roving mic.
Oh,
But I think
Sorry.
we're okay.
all right.
If anyone online has another question, either put your hand up or just start speaking. Otherwise, we're going to wrap it up. And I'd just like to say thank you to yes.
Thank you.
Prof. John, are you able to share the presentation?
Yeah, go ahead.
Yes, I just wanted to check. Are you able to share the presentation?
As far as I know, it was recorded and will be posted to the YouTube channel, the Wits Geoscience YouTube channel.
All right.
Okay?
Thank you.
Yep.
Okay, thank you.